Hello everyone, welcome to MEMONEET. This is Aprajita, your chemistry SME. How are you all doing and how is the preparation going on? So I hope the preparation is going well because now the time is getting lesser and lesser and we have to buckle up our seat belts and we need to work hard on our goal, right? So today I am back with another video on the P block element. So in the last video we have learned about the group number 13, 14 and 15 elements, that is the boron, carbon and nitrogen family. So today we are going to cover group number 16, that is the chalcogens, group 17 halogens and group 18, that is the noble gases. So as you know that this chapter more of involves theoretical things which you have to remember, the reactions, shapes, orders mainly. All right, so all of these we will be focusing on and I have taken the important topics of each group. All right, so without wasting any more time, let us start with group number 16. So you know that group 16 are the oxygen family, or you can say chalcogens, oxygen, sulfur. So we have oxygen, sulfur, selenium, tellurium and polonium. These are the members of group 16 and they are also called as chalcogens. So just like we have learned in the last session, here the outermost electronic configuration will be ns2np4, means they all have 6 electrons in their valence shell. Alright, now when we are moving down the group, the number of shells are increasing. So the atomic and ionic radii increases from top to bottom. No such anomalous behavior, no such exception. But you know oxygen size will be exceptionally small, of course, because it is in the second period and so its size would be small. So if the atomic size is increasing, ionization enthalpy decreases down the group because of the increase in size. But you should know, yesterday also I told you in the last video that the elements of group 16 should have higher ionization enthalpy, but they have lower ionization enthalpy as compared to group 15. Let's say if I am comparing nitrogen and oxygen, so oxygen is on the right hand side of the periodic table, so it should have higher ionization enthalpy, but because of the stable electronic configuration, this is not the correct order. Okay, the correct order would be nitrogen will be having greater ionization enthalpy. And what is the reason? The reason we have just studied yesterday, because of the half filled subshell. Here it is 2p3, here it is 2p4 and half filled is extra stable. So it happens with all of the group 16 elements. Okay, now because of compact nature of oxygen, its electron gain enthalpy will be less negative than that of sulfur. Okay, just like we did for yesterday. And sulfur onwards, the value again becomes less negative up to polonium. Now you know fluorine is the most electronegative element, so oxygen has the highest electronegativity after fluorine. Okay, and within the group electronegativity decreases. When we are moving down the group, electronegativity will decrease, means metallic character increases from oxygen to polonium. So oxygen and sulfur are non-metals, selenium and tellurium are metalloids and polonium is a metal. So you should know polonium is actually a radioactive substance. It's short-lived. Its half-life is 13.8 days. And all these elements exhibit allotropy, means they exist in different forms. Like oxygen ke liye we have oxygen gas, dioxygen, then we have ozone, right? Sulfur also exists as monoclinic, rhombic sulfur, like all of that. So these are allotropes. Then melting and boiling points, it increases with increase in atomic number down the group. All right. And oxygen exists as diatomic molecule, sulfur exists as a polyatomic molecule. It exists as S8. Now let us talk about the chemical properties. So since there are 6 electrons in the outermost shell, they will gain 2 electrons to achieve the nearest noble gas configuration. So the oxidation state, general oxidation state shown by them should be -2. But the stability of -2 oxidation state decreases down the group. Why? Because the metallic character is increasing. Okay, so that is why polonium hardly shows -2 oxidation state. And all you know oxygen is highly electronegative, so it will only show negative oxidation state. Just exception is OF2, because when it is forming a compound with fluorine, fluorine is nevertheless more electronegative than oxygen also. So in that case, the oxidation state of oxygen will be positive. Otherwise, it is electronegative, so its oxidation state would be negative always. But other elements, they show +2, +4, +6 oxidation states as well, and +4 and +6 are most common. Sulfur, selenium, tellurium, they usually show +4 oxidation state with oxygen and +6 with fluorine. And as we are moving down the group, the stability of +6 oxidation state decreases and +4 oxidation state increases. Why? Again, because of the inert pair effect, that is reluctance of s electrons to participate in the bonding. And bonding in +4 and +6 oxidation states is covalent. Now next is reactivity with hydrogen. So it is important. So they form hydrides of the type H2E. Alright. So here the question is usually asked on the acidic characters. So you should know that acidic characters of the hydrides, it will increase from H2O, then H2S, H2Se, okay, then H2Te. So it is going to increase. The increase, it is because of decrease in bond dissociation enthalpy for the hydrogen and this element bond, because as the size increases, that this bond weakens and the bond dissociation enthalpy decreases. So this hydrogen can be removed easily. That is why the acidic character increases. Okay, and if this bond can be broken easily, that is why the thermal stability of the hydrides also decreases from H2O to H2PO. This is what you should know, the thermal stability and the acidic character. Then reactivity with oxygen. So all these elements form oxides of EO2 and EO3 types like sulfur, selenium, tellurium or polonium. Ozone and sulfur dioxide are gases while selenium dioxide is a solid. Okay, and reducing property decreases from SO2 to TeO2. You should know that SO2 sulfur dioxide is reducing while tellurium dioxide is oxidizing agent. Okay, and they also form oxides of EO3 type like sulfur trioxide, selenium trioxide and tellurium trioxide. Then if I am talking about reactivity towards halogens, so they also form halides of type EX6, EX4 depending on the oxidation state, right? We saw na ki oxidation state can be +2, +4, +6. But you should know that the stability of the halides decrease in the order fluorine, chlorine, bromine, iodine. Okay. Next up, if I am talking about oxoacids of sulfur, just like we discussed the acids of phosphorus, so you can see that here sulfurous acid is H2SO3 and its basicity will be 2 because there are 2 ionizable hydrogen atoms. Okay, this is the structure. So structure you should know. Then H2SO4, again its basicity would be 2. Then peroxodisulfuric acid ka structure, here you can see that there is a bonding between the two oxygen, alright, H2S2O8. Then pyrosulfuric acid, which we call as oleum as well, H2S2O7. So these structures you must know. Then if I am talking about group 17 elements, so we know group 17 elements are the halogens. Okay, halogens, fluorine, chlorine, bromine, iodine and astatine. So astatine is actually we don't study that much, all right, because it's a radioactive element. We study fluorine, chlorine, bromine and iodine, and there are a lot of similarities in themselves, okay, just like group 1 and 2. Okay, and these kind of similarities we have not found in other groups, all right. So all these elements, they have 7 electron in the outermost shell, Ns2np5, which means they are just 1 electron short of the nearest noble gas, which makes them highly reactive non-metals. Alright. So they have smallest atomic radii. You know, when we move left to right in the period, atomic radii decreases. So here the nuclear charge is maximum because 7 electrons in the outermost shell. So they have the smallest radii. Okay. Just like other elements of second period, radius of fluorine is very small, okay. And when we are moving down the group from fluorine, chlorine, bromine, iodine, the atomic size increases because of the increase in number of shells. Now they have little tendency to lose electrons. Of course, they have 7 electrons, so they want to gain electrons. So that is why they have high ionization enthalpy, that a lot of energy would be required to remove the electron if in any case. Okay. and ionization enthalpy will decrease down the group, again because of increase in atomic size. Now, if I am talking about electron gain enthalpy, so now this is going to be high and it is going to be highly negative. Okay, means a large amount of energy is released when halogens gain electron, because they are just one electron less than stable configuration. So that is why they have maximum negative electron gain enthalpy, and this will become less negative as we move down the group, means energy will decrease. But you should know that the electron gain enthalpy of fluorine is less than that of chlorine. Ideally it should be chlorine, should be less than fluorine, but that is not the case. Why? Because fluorine atom is small in size. When electron gets added, so the orbital is 2p orbital. So in 2p orbital there would be electronic repulsions. In inter-electronic repulsion, electron will repel, so that will decrease the stability. That is why the electron gain enthalpy is less. But then if I'm talking about chlorine, so in chlorine the electron will go in the 3p orbital. So in 3p subshell or in 3p orbital, the incoming electron will not have that much repulsion, so it will experience much interaction. So yahan pe this is the important thing you should know, that chlorine will be the one which will be having maximum negative electron gain enthalpy. It will not be fluorine, it would be chlorine. And you should know that these elements are highly electronegative and electronegativity decreases down the group. And fluorine, yes, it is the most electronegative element in the periodic table. Alright. Okay, so let us move ahead now. Now if I am talking about the physical properties, so there is a smooth variation in the physical properties for halogens. Alright. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid, and melting and boiling point also increases with increase in atomic number. Alright. Next is students, all halogens are colored because of the absorption of radiations in visible regions. So excitation of outer electron takes place, and that is why the halogens are colored. Okay, so they display different colors. Like fluorine has yellow, chlorine has greenish yellow color, bromine is a red color liquid, and iodine has violet color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water, but they are soluble in various organic solvents, like we have chloroform, carbon tetrachloride, carbon disulfide. Okay. Now, just like I told you that this thing, your electron gain enthalpy of chlorine would be the highly, like, most negative. Now here you should know that if I am talking about the bond dissociation and enthalpy of the XX bonds. Okay, so as the size increases, the bond dissociation enthalpy decreases. Okay, but again the bond dissociation enthalpy of fluorine would be less than that of chlorine. Why? Because of the repulsions. Because of the repulsions, electron-electron repulsions, the like electrons, they are closer, right, in the case of fluorine rather than chlorine. So that is why the bond will be weak and the bond dissociation enthalpy is less. And then it follows the same trend: chlorine, then bromine, then iodine, means again the bond dissociation enthalpy of chlorine would be the highest. All right. Now students, we know all the halogens exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit +1, +3 and +5 and +7 oxidation state. Like here you can see NS2 NP5 is there now. So +1 or -1 oxidation state here they can show. Now if one electron goes to the d orbital, so here we have 3 half filled orbitals, so +3 oxidation state. Again if 2 electrons go like they get excited, so +5 oxidation state. And then if another one gets excited, okay, so here it should be one only, so if another one gets excited, so it can also show +7 oxidation state. Okay. Now like in interhalogen compounds, usually it happens that they show these higher oxidation states. So fluorine has no d orbital, that's why it cannot expand its octet. So being the most electronegative element, it exhibits only -1 oxidation state. And you should know that halogens are highly reactive. They react with metals and non-metals to form halides, and reactivity decreases down the group. Means fluorine will be the most reactive, then chlorine, then bromine, and then iodine. Okay, why? Now let us talk about the acceptance of electrons. So they can accept electrons. If they can accept electrons means they can get reduced. If they can get reduced means they are strong oxidizing agents. Okay. So fluorine is the strongest oxidizing halogens. Alright, and it oxidizes other halide ions in solutions or even in solid phase. Okay. So it is the strongest oxidizing agent. Okay. And decreasing oxidizing ability, you can tell from the standard electrode potential. Also we have studied about this thing as well. All right, so fluorine also oxidizes water to oxygen, whereas chlorine and bromine, they will react with water to form hydrohalic and hypohalous acids. Now these products you should know ki when fluorine will react with water, what you will get? You will get oxygen gas. Okay, and if other halogens react, so you will get the hydrohalic and hypohalous acids. Okay, this is what you should know. All right. Now reactivity towards hydrogen. So they form these halo acids. Okay. HX they will form. Okay. But affinity for hydrogen will decrease from fluorine to iodine. Why? Because the size of iodine is bigger, and also it is less electronegative. So that is why if I am talking about the acidic strength, so HF will, like, hydrogen and fluorine will be strongly bonded in this case, right? Because of high electronegativity of fluorine plus small size. But as we are moving downward, size increases, so X bond becomes weaker. So that is why the bond enthalpy decreases in the order and the acidic character increases. All right, and if I am talking about the reactivity towards oxygen, so they form many oxides with oxygen, but most of them are unstable. Fluorine forms OF2 and O2F2. Okay, but OF2 is only thermally stable. Okay, so these are oxygen fluorides because of high electronegativity of fluorine. Okay, so this you should note. And chlorine, bromine and iodine, they will form oxides in which oxidation state will be from +1 to +7. Okay. Now we have higher oxides of halogens. They tend to be more stable than the lower one. So we have chlorine oxide, Cl2O, then ClO2. Different types of oxides are formed. Okay, they are highly reactive oxidizing agents and they tend to explode. ClO2 is used as a bleaching agent for paper pulp and textile industries. Bromine oxides are least stable halogen oxides. Okay, and they exist at low temperatures only. They are powerful oxidizing agents. And iodine oxides are insoluble solids. They decompose on heating. Okay, so we are talking about every halogen here. Then you should know that reactivity towards metal. So like magnesium plus bromine, they will react together to form magnesium bromide. Okay. All right. So like this, they will form magnesium bromide. Okay, and ionic character of halides decreases in the order MF, MCl, MBr and Mi. Means the ones with fluorine will be the most ionic. All right. Towards other halogens, you know, halogens combine with themselves, means they combine with other halogens to form interhalogen compounds. Okay. Next, oxo acids of halogens. So because of high electronegativity and small size, fluorine forms only one oxo acid, which is HOF, which is called fluoric acid or hypofluorous acid. But you can see others are formed like chlorous acid, then chloric acid, perchloric acid. So the structures are like this: HOCl. Okay, then HOCl, then double bond O. Then we have HOClO3 as well. Let me show you how it looks. Okay, so in this case, like, it would be like this: HOCl Cl double bond O double bond O. So this will be HOCl3 per chloric acid. Similarly, we have bromic, perbromic, iodic and periodic acids. Okay, now let us talk about group 18 elements. So group 18 elements have 6 elements: helium, neon, argon, krypton, xenon and radon. So you know these are all noble gases because these are unreactive gases. Why they are unreactive? Because their outermost shell is completely filled. Ns2np6, they have 8 electrons except helium, of course, which is 1 is 2. Okay. Now, because of stable electronic configuration, high ionization enthalpy, however, it will decrease when we move down the group. Atomic radii also increases because of course number of shells are increasing. Now you know noble gases have stable electronic configuration. So do they want to accept electron? No, right? They don't have any tendency to accept electron. So what about the electron gain enthalpy? So it means we need to provide energy for a noble gas to accept electron. So it means they will have large positive values of electron gain enthalpy. Okay, noble gases are monoatomic, colorless, odorless, tasteless. They are sparingly soluble in water. They have low melting and boiling points because there are no interatomic interactions. Okay, so it's just that only weak dispersion forces are there. Helium has lowest boiling point of any known substance. Okay, 4.2 Kelvin. All right. So you know, since noble gases are have completely filled outermost shell, so they are least reactive. Okay, so they have Ns2np6 configuration, so they have high ionization enthalpy and positive electron gain enthalpy, but some compounds were found. Okay, so actually there was a scientist, Neil Bartlett. All right, he observed the reaction of noble gas. He prepared a red compound which is formulated as O2 plus PtF6 minus dot He. Okay, so then he was actually doing this research and he found out that first ionization enthalpy of molecular oxygen was identical with xenon. So that's why he made efforts to prepare same type of compound with xenon. So usually the compounds that we get are xenon compounds. Okay, mostly you will find xenon compounds. All right. So and that too with the electronegative elements like fluorine and oxygen were synthesized. Okay, and compounds of krypton are fewer. Only krypton difluoride has been studied in detail. Okay, and radon compounds have not been isolated. And for argon, neon, helium, no true compounds are known yet. So mainly the compounds of xenon are known, like we have fluorides XeF2, XeF6, XeF4. Okay, by direct reactions of xenon and fluorine gas under experimental conditions. You can see XeF6 can also be prepared by the interaction of XeF4 and O2F2. So these are colorless crystalline solids and they sublime at 298 Kelvin and they are powerful fluorinating agents. So we can use them as fluorinating agents. Fluorinating agent means when we have to add fluorine to any compound. Okay, they are hydrolyzed even by traces of water, like XeF2 hydrolyzes to give xenon, HF and oxygen gas. Okay, now the structure of these fluorides, we can find them from the Vesper theory. We have studied valence shell electron pair repulsion theory, right? So XeF2 and XeF4 have linear and square planar structures. Like how will you find out? See XeF2, if I am saying, so only two fluorine are there, means only two bond pair will be there, and but xenon has 8 electrons, so right, 6 electrons will be there as 3 lone pairs. So of course the shape would be linear like this and there will be 3 lone pairs. Okay, and XeF4 will have a square planar shape and 2 lone pairs would be there. XeF6, which has 6 bonding pairs and 1 lone pair, will have a distorted octahedral structure like this, you can see. Okay, so then we found some xenon oxygen compounds also, like hydrolysis of XeF4 and XeF6 gives XeO3. Okay, and this compound was found out. Then partial hydrolysis of XeF6 gives oxyfluoride. So oxyfluorides are also there, XeFO4, XeO2F2, and these are the structures here you can see. So for only we will be studying xenon compounds. In this case, you should know a little bit about their shape as well. Okay, and these reactions. So students, with this we have covered all the groups up to group 18. So I told you, remember the trends, whatever we have discussed, some exceptional behaviors are there, and the reactions you have to memorize. All right. And if in case you are having any doubts, please do let us know through the comment section. Okay, if you want me to explain anything else or anything that is not clear, I'll explain it in another video. All right, and all the best for your next BPT. Okay, do well in that, and in case any doubts, please feel free to tell us. Thank you so much. Bye bye.